Welcome to this explainer. Today, we are skipping the basics and jumping straight into the incredibly high-stakes, high-tech world of advanced exploration and formation evaluation. We're going to look at exactly how modern geology meets cutting-edge engineering to basically find, evaluate, and safely extract hydrocarbons that are hidden deep underground. It is kind of like trying to break into a giant, locked vault miles beneath our feet.
Okay, let's dive into this. Here is our treasure map for today. We'll start out by evaluating the basin, move into the wildcat gamble, get our hands dirty extracting core samples, spend some time decoding well logs, and finally, wrap up with surviving pressure regimes.
Section 1. Evaluating the basin. Let's take a look at the geological assessment.
So before we even think about putting a heavy, wildly expensive drill bit into the ground, we have to zoom way out to the macro level. Think of this stage as being geological detectives. Basin evaluation is a really broad assessment of sedimentary basins, and we are looking for very specific clues here. We need to evaluate source rock maturity, which is essentially checking if Mother Nature's slow cooker has baked the ancient organic matter long enough and at exactly the right temperature to actually create oil or gas. We also have to map out migration pathways and structural traps to figure out where those hydrocarbons might have flowed and accumulated over millions of years. This whole step is all about confirming the total commercial potential before any massive financial gambles are made.
Moving on to Section 2, the wildcat gamble, high-risk, high-reward exploration. Once we've evaluated that basin and identified a promising trap, it's time to take a massive leap of faith and put real money on the line. So the crucial point here is the intense economic stakes involved in this step. Wildcatting means exploratory drilling in completely unproven or unmapped frontiers where absolutely no existing field production exists yet. You might be in a remote, incredibly harsh onshore location or out floating on a highly complex rig in deep water environments. You are risking tens, sometimes hundreds of millions of dollars on a single well solely on the chance that your basin evaluation was right. It is literally the ultimate high-stakes gamble.
Section 3. Extracting core samples. This is all about physical rock retrieval.
Okay, let's say our wildcat, actually reaches the target depth. Awesome. But we don't just immediately start pumping. We need to gather our physical clues first. But how do we actually get them? Well, we generally have two methods, conventional hole cores and sidewall cores. Let's draw a really clear line between the two. Conventional coring means we're extracting these massive, continuous chunks of rock as we drill downward, giving us a beautiful, intact vertical timeline of the geology. Sidewall coring, on the other hand, is literally punching out smaller, localized samples from the side of the wellbore after it's already been drilled. Both methods give us the physical rock we desperately need to analyze.
And this brilliantly illustrates what happens next. Once we have the rock, it heads straight to the lab to measure its exact properties. We're testing the mineralogy to see exactly what the rock is made of. We test the permeability, which is simply how well fluid can flow through that rock. And most importantly, we test porosity, specifically looking at the difference between absolute porosity and effective porosity. Absolute is the total empty space in the rock. Actually, scratch that. Think of it more like the total potential empty space. But effective porosity tells us if those pore spaces are actually connected to one another. Because if they aren't connected, the rock can't actually flow or hold recoverable oil.
Section 4. Decoding well logs. Time to use some wireline and LWD tools. Physical rocks are fantastic, absolutely, but getting them can be slow, and we really need a continuous picture of the entire wellbore. This is where we transition from physical clues to taking what is basically an actual MRI of the Earth. Well logging means we lower these incredibly sophisticated instruments down the hole to record physical properties as a continuous function of depth. It's like a cheat sheet for the subsurface. First, the gamma ray tool measures natural radioactivity, which perfectly distinguishes lithology, separating the non-reservoir shales from the highly desirable sands. Next up is resistivity, which blasts an electrical current right into the rock to see what kind of fluids are hiding down there. Hydrocarbons resist electricity while salt water conducts it. Finally, we have density and neutron logs, which work together to calculate the rock's porosity without even needing the physical core.
Now, what's really interesting about this is that the real magic happens during log interpretation. We don't just look at one tool in isolation, we analyze all these overlapping data tracks together. By comparing the gamma ray, resistivity, and porosity logs side by side, we can identify the exact pay zones, the specific layers of rock that will actually produce hydrocarbons. We use these overlapping tracks to calculate our water saturation, or SW, which tells us the exact ratio of oil versus water trapped in those pores, and that helps us estimate the net effective pave thickness of the entire reservoir. I want to slow the pacing down for just a second here, because the technical mechanics of reading these track-by-track curves can reveal some incredible hidden secrets. When you overlay the density curve and the neutron curve on top of each other on the log, they normally track somewhat closely together if the rock is filled with oil or water. But if you hit a zone filled with natural gas, boom, the two curves will pull wildly apart, crossing over each other in completely opposite directions. This is called the crossover effect. It acts as a glaring neon sign on our well log, instantly and brilliantly separating a gas zone from an oil zone.
Which brings us to Section 5, Surviving Pressure Regimes. Finding the oil and gas, that's really only half the battle. We also have to survive getting it out, which means navigating the physical dangers of unexpected booby traps thousands of feet underground. When we're drilling, we encounter three main subsurface pressure environments. First is normal hydrostatic pressure. This is what we expect, just a normal, predictable weight of the fluid column above us. We also have underpressure, which is lower than expected. But the real danger lies in the middle of this list, overpressure, or abnormal high pressure. This can happen due to phenomena like compaction disequilibrium. That's a fancy way of saying fluids get trapped in the rock as it's being buried over millions of years, squeezed tighter and tighter without any way to escape. Drilling blindly into this zone is a fantastic way to let Mother Nature violently push fluids right back up your wellbore. No thank you.
This is exactly why properly evaluating those subsurface pressure environments ahead of time is absolutely critical for well control. The primary defense we have against overpressure is the dense drilling mud that we circulate in the well. By selecting the optimal mud weight, we exert enough downward hydrostatic pressure to keep those volatile formation fluids securely in their place. But if we get the math wrong on those pressure regimes and our mud weight is too light, we risk a truly catastrophic blowout at the surface.
Let's zoom out and see how this all builds together. When we look at the entire life cycle, the strategy is pretty clear. We start our hunt with Step 1, basin mapping to find the commercial potential. We risk it all in Step 2 with wildcat drilling. We prove the treasure is actually there in Step 3 using core and log analysis. And we manage the severe physical realities in Step 4 with strict pressure control. This entire sequence links macrogeology directly to microscopic physical measurements, and it all converges for ultimate field development.
It's an incredible, high-tech process that beautifully bridges geology, physics, and engineering. But it leaves us with a fascinating question to close out this explainer. As we push into even more extreme frontiers, deeper waters, harsher environments, and tighter rocks, how will these formation evaluation techniques evolve? What will the future of high-tech exploration and Earth MRIs look like as the economic and environmental stakes get even higher? Keep that in mind the next time you see a drilling rig on the horizon. Thanks for joining me on this deep dive, and I will catch you on the next explainer.